Finding the median from a data stream. The median is the middle value in an ordered integer list. If the size of the list is even, then there's no middle value, and the median is the mean of the two middle values. And they give some examples, and they want you to implement it as a class with a couple of functions. One for inserting elements into your whatever data structure you're using, and then something to actually return the median at any time. So they could say, give you a few numbers, then find the median, give you another number, find the median, give you a few more numbers, find the median, so that you got this kind of data stream that's a running thing. It says there'll be at least one element in the data structure before calling find median. Okay. Anyway, so I'll talk about the solution before I talk about a common mistake that happens a lot. The solution is to use two min heaps, or you use a min heap and a max heap, and you have one of them hold the lower half of the data stream and the other one hold the upper half of the data stream. That'll give you constant time retrieval of the median itself, and then it'll give you logarithmic time to insert a number into the the storage. It's going to be O of n space, log of n time per number, so a total of O n log n. And you can achieve the exact same theoretical bounds if you're using, say, a vector and binary searching through it to find where you want to put a particular number. The reason that I don't think is a good idea is because if you mess up handling the array and you don't know where a particular number should end up, you're gonna run into an n squared time, because if you need to insert a number but there's no space for it in this, if you're doing just an array and binary search, then you're gonna have to copy pretty much all of the numbers potentially over to another part of the array, and that becomes an O of n time operation instead of log n time. So that's why we want to use the priority queues, because they don't have that problem. Yeah, other than that, this problem is mostly just a check on knowing the data structure to use. It's not particularly clever algorithmically. It's just two priority queues, and your median is the value from one of them, or if they're the same size, getting the mean of the two. So heaps in C++ are in the queue header, and they're called priority queue. And we're going to hold integers with it. And one of them I'm going to call Q low, and the other one I'm going to call Q high. All right, so this lower priority queue that's going to hold the lower half of our numbers, we want the highest element to always be at the front of the queue. This other one that's going to hold the upper half, we want the lowest element. So we're going to need to use a different non-default comparator. In order to do that, we need to know the template arguments. So the first one is obviously the type of data that it's holding. That's a little more intuitive. And then you need a second one, and that's a container. I've never seen it not be a vector, but you still need to put it in order to get to this third argument, which is going to be our comparator. And this is all you need if you're not initializing any values into your queue. It's just going to start empty. This is what tells it to put the lowest item at the queue. So priority queues, usually the comparator needs to return a Boolean, where I think if the left, it'll return the left value if it's, I guess, greater. So I'm trying to remember this. It'll return the left value if the answer is false. And it'll return the right value if the answer is true. I can't remember. But by default, it's going to put the highest thing out. And instead of trying to tell you something and getting it wrong, or pulling up documentation, which takes forever, I'm just going to tell you that in order to show the priority queues, highest item is default, lowest item, you need to use this custom comparator. All right, so let's write out our add function. So what it's going to do is first we're going to say if the lower, so by convention I'm going to choose to have my median be in the lower queue if their sizes are different. So first we're going to check if it's empty, and if it's not, we're going to compare our number to the first item on that queue. All right, so if it belongs in the lower queue, we're going to add it to the lower queue. Otherwise, we're going to put it on the higher queue. That could still end up with the two queues being imbalanced. So for example, let's see, would it? Possibly. If it adds every single number being the same, so the first number, it's all just like the input is say all ones, every single one is going to go into this lower queue. So we do need to have a balance step so that their size, we don't want their sizes to always be roughly equal. So balancing is going to add another constant number of O log n operations to the addition. That's not going to change the theoretical limits. It's just going to add another constant. So while q low dot size wait, so q, if it, so we're working on the case if the q low is bigger. Q high. Right, so if there's an odd number of elements, we want this one to have one more item, and if there's an even number, we want their sizes to be even. So it's okay if this is slightly bigger, but it's not okay if it's more than one bigger. So q high dot push, q low dot top, and then q low dot pop. And then I don't know that it's necessary to add a balancing step in the other direction. Let's see, if it's always adding numbers that, so if num is less than or equal to top, so if it's always adding numbers that are bigger, you'll see you're pushing things from the low queue to the high queue in this case. And if you're always adding items that are bigger, could you ever come up with a case where you could have the high queue have more things in it? I'm going to leave it out, and then maybe I'll add a balancing step in the opposite direction as well. That would certainly be safer. And realistically, I'll go ahead and add it because I'm not really planning to step through an example on this one. It's a little bit of a simpler algorithm, and it's really just knowing the data structure and knowing the library calls. While q high dot size is greater than q low dot size. Q low dot push. Q high dot pop. Yeah, that'll work. So then for this, we need to return a couple of things. We need to return a double, so we're converting from integer to double. We can use implicit conversion, but to do that, I am going to make a double temporary variable. I'm going to call it ret for return. If the small one is bigger, so q low dot size return, yeah, I'm using this temporary variable for the purpose of implicit conversion. Q low. Okay, I don't need these braces after all. Too many. Makes it hard to read. Right, so what this is doing is, if they're the same size, then it's taking their mean. And if they're not, then it's taking the one just in the lower queue. All right, so I'll write out the run times, but I am going to skip the example. So it's going to be O of log n per insertion, so per call of add num. And then it's these push, each push and pop call is logarithmic. The top calls are constant time. And you might do one. These while loops are realistically only because of this if else condition. That's how we know that while is going to do one, maybe two iterations before it's done. So there's an upper bound. It's not going to keep going. It's going to be one or two. So that's a constant number of iterations to do this logarithmic thing. So we end up with a constant number of logarithmic operations per add num call. So it's logarithmic overall per insertion. And n log n total. And then it's going to be O of n space. Since we are using our own data structure and we're storing every element that comes in, it's going to be in one queue or the other, but the total is still going to be linear space. There's not really a way to do it with less than that, because we can't say discard non-median elements just in case, say, we still need to know where a new number is going to fit in the total line, so we know which way to kind of shift the median, I suppose. So we do have to save them all. There's not really a way to do better than that. I think that's pretty much it. Let's give it a run for syntax. Typo. Character 19, line 40. What did I do? This. Yep. And then get rid of that. Cool. And then submit. Nice. And lastly, we mark it off. Thanks.